All right. Well, welcome, CFAW. Seems like there's just one CFAW. I 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. I mean, there's at least 8 people who should not be here who are here. I mean, well, it's CFAW's pre-game. Yeah. All right. I mean, if you want to be here, it's fine. I'll begin with a prayer. Dear Heavenly Father, we thank you for this day. Thank you for some of these students, and help us to glorify you what we do this day, Lord. In your name I pray. Amen. Let's see here. So. All right. So we were talking about field extensions, right? And so there was another theorem that I should share with you guys, Theorem 8. And it says if we have phi mapping from one field to another, an isomorphism of fields, all right. And if we have p of x be a polynomial over the field, irreducible, and p prime of x, not the derivative here, but p prime of x and f prime of x obtained. Let me just explain what it is via the following. So if p of x is equal to, let's say, an x to the n plus plus a1x plus a0, then p prime of x is the corresponding polynomial, which we obtain from just mapping the field coefficients. So like, instead of having an as the leading coefficient, we have phi of an, x to the n, and then phi of a1 x plus phi of a0, right? And so each one of these coefficients are in f prime, right? So this is an element of f prime of x. In fact, this describes a homomorphism, right, from fx to f prime of x, the induced homomorphism. So I'm starting with a homomorphism, rather an isomorphism of the fields, and I'm saying that also gives us a corresponding homomorphism of the polynomials by this rule, all right? And furthermore, let alpha be a root of p of x, all right? He says in some extension of x, in some extension of f, all right? And we let beta be a root of p prime of x in some extension of f prime, all right, then there exists isomorphism sigma going from f adjoin alpha to f prime adjoin beta, defined, given by alpha maps to beta, right, and extending phi. I mean, more specifically, here's the picture of what the theorem's claiming exists. We have, let me start with what we're given, okay? We're given this isomorphism down here from one field to another, all right? That's given. And then there were 13. Let's see, committing to the joke. She does not have the will of fire to commit to the joke.
She has an appointment.
Appointment. Yeah, likely story. Let's see. We all have priorities. Let's see here. So, isn't that what Soprano says? Let's see here. So, and we're also given that, I mean, there's some root of P of x. Now, why does P of x is assumed to be irreducible, right? Which means it has no root in what? In the field, right? Unless what? It seems like there is one kind of polynomial that's irreducible in the field and yet has a root. Isn't x minus c irreducible? Right? So I suppose to make it, well, anyway, that doesn't mean you can't extend by the root. It's just what would, if we extend by a root that the polynomial already has, what's the extension? Like if I take the real numbers and extend by the square root of 2, what do I have? I take the real numbers, I adjoin the square root of 2 to it, what do I have? I take the real numbers, I adjoin pi to it, what do I have? The real numbers, right, because they already have those things. Yes. It's not complicated. And then over here, f prime adjoin what? Beta, I think he said. So we're given all this data. We've got two fields. We have an isomorphism between them. We have a alpha is, here p of alpha is 0. Over here, p prime of beta is 0, right? By construction, these are roots. These are extension fields of f and f prime respectively, in which p of x has a root, in which p prime of x has a root. Then this theorem says that there exists an isomorphism between these, right? That there exists this sigma here. So I would actually tend to not write these over here. I prefer to write this diagram like follows, just to put the phi here and put the sigma here, like that. The vertical lines, what are those? That's what we were talking about the last couple classes, this, like assignment of f fitting inside the extension of f, or f prime. All right, so what does this mean? I mean, this is a little bit vague. What's the relation between the sigma and the phi? So sigma of, this much I can tell you, sigma of alpha is equal to beta, right? And if we take sigma and restrict it to f, what do we get? So sigma restricted to f, if we look at, anything in there, let's say c, we're just going to get what? We're going to get phi of c for all c and f. More generally speaking, what does a typical thing in alpha alpha look like? F adjoin alpha here. Because my p of x is nth order, what did we learn? It's like a vector space of dimension n over f, right? It looks like something like c0 plus c1 alpha plus c2 alpha squared plus plus cn alpha to the n minus 1, n minus 1, such that c0 through cn are where? n minus 1. I have trouble with this numbering, don't I? Curses. Cn minus 1, yeah. Where are these? These are in the field, right? This is what the extension by alpha looks like, right? And so to describe this mapping isomorphism phi precisely, I should tell you what does sigma do to this? Now, Dummett and Foote has the good sense to not write this out. I'm just writing it out for you. How would sigma act on an arbitrary element of f adjoint alpha? What does it do? It just changes the alphas to what? To betas. And what does it do with the constants? Yeah, so yeah, exactly. So it's phi of C0 plus phi of C1 beta, phi of C2 beta squared, plus phi of Cn minus 1 beta to the n minus 1. And the claim is that this is an isomorphism. All right? Now, how does he prove that this is an isomorphism? Well, it's very simple. What he does is he just says, we induce, let's say, phi tilde from f adjoint x to f prime adjoint x as I've described. All right? So like phi tilde, this would be phi tilde of p of x, okay? Phi tilde of, you might want to pan back over here, Sarah. This is phi tilde of p of x. It's the natural assignment of p of x to a corresponding polynomial in f prime of x, right? That's the extension of phi to polynomials. Okay, so that's a homomorphism, and he points out that p of x is maximal in f of x, and he's also argued that phi tilde of the maximal ideal generated by p of x is equal to the maximal ideal generated by the irreducible polynomial p prime of x. All right? So you put these things together, and if you look at f of x mod the maximal ideal p of x, well, that would be isomorphic to f prime of x mod the maximal ideal p prime of x. Because what are we looking at here? So cutting through, yeah.
The line with the p tilde, is that saying the ideal generated by p of x for both of them, or is it actual print?
The ideal. Yeah, fine, fair enough. There you go. Go back to wrangle. Sorry.
Much more sense.
Well. Oh well. So.
Wait, so they both, is it? I don't know what's correct.
You guys can write Langle if you want. Okay. So in fact, this is f of alpha, that's f prime of beta, and they're isomorphic because we can just use this map to see this. Let's see here. Anyway, so actually what I really wanted to talk about is, when I first read this theorem and I sorted through the proof, which is in Dummett and Foote on, page 519 or so, it kind of left me going, huh? Like, what does this matter, where this matters most and where it's most interesting is when we take the case of phi being the identity map. All right, so the application that I think is interesting is when we take just phi going from the field to the field, and just phi of x equals to x. Well, x is a bad choice here. Phi of a constant equals to the constant for all constants in the field, right? Because what this says is that, for example, if I look at p of x equal to x squared plus 1, which of course is irreducible real polynomial, right? Then, this is not especially surprising, but notice that p of I equal to 0 and p of minus I is equal to 0. So we could think about alpha equals to I. We could think about beta equals to minus I. These are two different extensions, right? And so, here's the picture. We have our parentheses I, parentheses, our parentheses minus I. These are extensions over the reals, right? And down here, we have phi equal to the identity. And up here, we have some sort of isomorphism, right? The theorem says that there exists an isomorphism. It doesn't really give you in some sense, it gives you what is the isomorphism exactly? It's, let's see here. So we would take, so we're talking about sigma of A plus BI. And how does it work? That's a typical thing in the extension by I, right? Because this is a quadratic, so it's a degree 2 extension over the reals. And so if we follow the theorem through, it says, okay, well, that's sigma of, not sigma, but what? Phi of A, right? Plus what? Plus phi of B. And then what happens with, how do we define the map? We map I to minus I. And so that is what? That's A minus BI. Or IB, if you like. Yes? I'll say BI.
Because it's a quadratic, why is it obvious that we're extending by A plus BI?
Oh, well, remember this, so let's see here. R adjoin I over R is equal to 2 because, p of x equals to x squared plus 1. This is the irreducible quadratic, which we're adjoining a 0 of, right? So if we have an irreducible polynomial of degree n, and we adjoin a 0 of that polynomial to our field, that extension is an nth degree extension. So quadratic, so it's degree 2. And degree 2 means that, generically speaking, I've got, 1 C0 plus C1 alpha, but that stops right there because the alpha is I, and that's as far as it goes because it's degree 2. No? Yes? Oh, you think so? Okay. I'll take a think so. But I don't think it's, at first glance, it's not obvious that this is talking about complex conjugation, is it? But it is, right? If we apply this to the case of the identity map on a field, it's saying that there's some sort of generalization of complex conjugation which goes from one root to another. Yeah.
So what would be like a degree 1 extension?
That would be quotient by the linear polynomial. A degree 1 extension, that would bring me back to my silly red comment. So if I took, say, R of x mod parentheses x minus 2, then this would be isomorphic to 1, well, it's kind of stupid, C0, such that C0 is a real number, which of course would be the real numbers. So, I mean, in other words, what you're doing in this quotient is you're essentially, morally, you're putting x equal to 2, you know? That's what's happening in that quotient. So if you put x equal to 2 in polynomials, what happens? Every polynomial just becomes a valuation at 2, really. Yeah. Which is a number.
What we're extending by, is it like technically 1 degree less than what we started with because of the way we constructed?
Because 1 is in the basis, it's always 1 degree less than what we're extending, yeah. Yeah, because 1 isn't, because we start with 1. Which is the thing, I get confused at the upper end of it, you know? I keep wanting to call this Cn, but my numbering should be Cn minus 1, right? Because it starts from 0. Another example that we already touched on, but I think it's nice to talk about that in the context of this theorem, is if we take the rational numbers, right? We take Q, right? Adjoin, well, you know, polynomials and rational polynomials, and we quotient by x cubed minus 2, right? So this is isomorphic to what? I mean, it's isomorphic to Q adjoin the cube root of 2, right? But it's also isomorphic to what? Q adjoin what? Like cube root of 2 e to the 2 pi I over 3, right? And it's also isomorphic to Q adjoin the cube root of 3, cube root of 2 e to the 4 pi I over 3, like you guys told me. And so applying this theorem again, if we have a picture, right? Here's Q, take the identity map for my phi. So extend to Q adjoin square root, cube root of 2. And then over here we have Q adjoin, I need to give this stupid thing a name, zeta. Fine.
I'm so bad at drawing this.
I'll make it a beta. How about that? There you go. All right. What's the isomorphism that goes from here to here? Like Q adjoin cube root of 2, what's that look like? This is a degree 3 vector space. So we get A plus B cube root 2 plus C cube root 2 squared, ABC rational. And this theorem actually tells us how to construct the isomorphism to Q adjoin beta. I'm saying beta here is equal to cube root 2 e to the 2 pi I over 3, just for the sake of specificity. And so the sigma of, let me just call this thing Pac-Man for the sake of not writing it again, Pac-Man, would be equal to what? It's equal to A plus B times cube root of 2 e to the 2 pi I over 3 plus C times the cube root of 2 e to the 4 pi I over 3. And that would be an isomorphism of Q adjoin root 2, cube root of 2 rather. And, oh no. Quiet. That was an email about something very interesting that I don't have time to think about right now. Curses. All right, but anyway, there's an isomorphism. The deeper thing here, guys, is that there's some sort of equivalence between these different roots of the polynomial, right? Because it doesn't, there's no algebraic difference between adjoining the cube root of 2 versus joining beta, right? They're isomorphic as fields, as extension fields, right? I mean, that's kind of surprising. If you start with a, 5th degree polynomial that you can't find roots for, right? and you find one root for it, and that, that describes a, 5-dimensional vector space over the original field, why should every one be like that? Why can't there be other roots that are like 3-dimensional vector spaces or something different? Why do they all have to look the same? This is surprising. It speaks to some sort of underlying symmetry between the roots. We understand that symmetry very well in the case of real numbers because it's complex conjugation, right? But what that symmetry is between the roots of a given polynomial, it's something different when we look at more exotic examples. Yeah? This isn't just complex conjugation, is it? But is it complex conjugation if we were to examine, let's say that, well, actually, what is beta conjugate? What do I use, stars or bars? Bar, okay. I always have to be reminded, as you guys know, I was raised by physicists. I mean, academically speaking. My parents are doctors, but, yeah. I mean, academically speaking. So the complex conjugate of e to the 2 pi I is what? It is e to the minus 2 pi I over 3, right? Which is what? Yeah, like you said. It is, if I add 6 pi over, can I add 6 pi over 3? That's 2 pi, right? 6/3 is 2. So adding 6 pi over 3 gets me to 4 pi I over 3. In other words, this, up to some arithmetic, which we're having trouble doing today, I mean, maybe I am, maybe I'm not. We can't say. But that's what? That's the other root, right? So in fact, complex conjugation is the isomorphism from here to here. Because these are both subfields of the complex numbers. So there we could actually just straight complex conjugate. What was it, Morgan? Yes, you need to know complex conjugation. That is true.
But like extending from q over 2 to q over 2 e 2 pi I over 3.
Well, that we should know. I tried to talk about that in 421. That goes back to the roots of unity stuff, right? I don't know where to start there. If we have, here's just a brief example. If we have f of z equals to, say, z to the n minus minus w naught. So then, if you want to, you can factor this into z minus z1, z minus z2, z minus zn for appropriate complex numbers z1 through zn, right? I know this happens by the fundamental theorem of algebra. There exists n complex root to a complex polynomial equation possibly repeated, right? So how do I actually find the z1 through zn? What you do is you take the w naught and you write it in polar form. So w naught can be expressed as like the length of the w, and then e to the I theta. So w is a complex number. So this is both complex polynomial, okay? So here, just a picture, if this is w, then the length of w is the modulus, and this is the angle theta. So if you think about w naught, it's u naught plus iv naught, and finding the length of that complex number and the standard angle is standard, really, calculus 3. You know this, right? So okay, you find that, and then the definition, the nth root, principal nth root of w naught, is by definition the regular plain old garden variety nth root of the modulus of w naught. This is the real nth root of that positive number, absolute value of W naught, length of W naught, and then you do e to the I theta over n. Right? This gives me a basic solution to the nth order polynomial equation. So this we could call Z1. Okay, you can easily check that f of Z1 is equal to 0. Because if you plug this up into that, you take the nth power of this, you get back the modulus of W naught, and this raised to the nth power by laws of complex exponents gives us back e to the I theta, but modulus of W naught times e to the I theta is W naught, and then W naught minus W naught is 0, which is this. Then the cool thing is, the rest of the solutions you can generate by multiplying by the nth roots of unity, the nth root of unity. Principal nth root of unity. What is that? That is e exponential 2 pi I over n, which I could write more briefly as e to the 2 pi I over n. You're looking too comfortable with this, let me give it a name, omega n. Ooh, betch, well, it's omega, it's clearly not the W, right? Fine. Zeta n, there we go. So Z2, you just take Z1 times zeta n, and then Z3, you take Z1 zeta n squared, and so forth. The jth one will just be equal to Z1 times the zeta n to the what? Looks like j minus 1. And those are the roots of this polynomial. Now, I mean, this is kind of a special case, isn't it? How do you factor a more general nth order polynomial? Like, what if it's not just z to the n minus w naught? What if the polynomial we're trying to factor, g of z, is, you know, z to the fifth plus the 3z squared minus z plus 7? What if instead of trying to factor, I mean, because I just factored a pretty nice polynomial, how would I factor that? How would I factor g of z equals to z squared plus bz plus c? See that? You should be able to just straight up factor. How do you factor that? Quadratic formula, right. I do z minus z1 times z minus z2, where what? Where z1 and 2 are equal to minus b plus or minus the square root of b squared minus 4ac, which is just minus 4c here, divided by 2. That still makes sense when b and c are complex numbers. This is something you prove in complex analysis, actually, or you should prove. I should have made it a homework. Did I make it a homework? I can't remember. Yeah? Oh, man. I was too busy doing the A calculus. See what you missed out on. I know. But in fact, that is a stone-cold formula. The completing the square thing that you do to derive it, some of you have experienced in real analysis. Yes? No? Yeah. How'd that go for you? You know where that came from? Did he explain? No. So some guy in the Math Educator Stack Exchange was like, how many professors could prove the Abel-Ruffini result? You know, and some guy's like, let's trade that question for a more shocking question. How many math seniors could derive the quadratic formula? So you never got it back? Some of you did. I can't remember what the answer. No, I just heard the results. But a guy at another school did it, and the results were, he gave it to like 30 people, kind of like you guys, and 15 people just left it blank. 6 people did whatever kind of stuff, and then there, I think, there were like 9 who actually did it, 4 or 5 of which worked it backwards. So I mean, this is kind of sobering, you know. You're math majors. This is the sort of thing that you should be introspective and take ownership over, you know. But I understand. Different people, you know, maybe just never happened for you. I don't know. But anyway, my point though is, when you go through that, actually it still makes sense. The steps in that still make sense when you flesh out the details over the complex numbers. So the quadratic formula is equally apt for complex coefficients, right? And but this over here, you know, what's the? I mean, if I had some formula, right, like the quadratic formula, where I could just write down z1, z2, z3, z4, z5. I know they exist, by the way. I know that there exist 5 zeros of this, because the fundamental theorem of algebra tells me that a 5th order polynomial over the complex numbers has 5 roots, possibly repeated. So they exist. I know they exist. I have arguments that they exist. But how do you actually find them for a generic 5th order polynomial, right? Now, the quadratic formula we've known for a while, I think since the Babylonians, or, you know, pick your favorite culture. You do the history. I'm not going to do history. People always argue. And then, what is it? These pesky Italians, the Tartaglia, and Ferraro, and what's the other one? Ferrari, was it? Ferrari's in there somewhere. You know, these guys, they came up with a formula for the analog of the quadratic formula for a cubic, right? The cubic formula. And then it wasn't long after that they came up with the quartic formula. My wife actually learned these things in high school. They worked them out in her A-level mathematics in Hong Kong.
Aren't they like really long?
They are long, yes. They're bad. I had an irreducible polynomial built over that stuff, constructed by Dr. Smith, that I almost put on your final. Or did I put it on your final? I might have. So yeah, I mean, there's a reason. There is a reason that you don't know the cubic formula, because it's lengthy, and the quartic is even worse. So, you know how people are. 2 works, 3 works, so by induction, 4 must work. Oh, it does work. So surely 5, 6, 7, right? We can find formulas, analogs for the quadratic formula for like a quintic, right, or a higher order polynomial equation. What would that mean? A formula would mean that the zeros can be formed by, like, maybe adding a radical of numbers, right? Like something like a square root of numbers. That's what we're doing here, right? This I is in some sense adding a radical. It's the square root of -1 in the other notation, right? So it's kind of like, I mean, we're doing a radical extension of the reals there. So maybe there's some sort of radical extension that we could do that, you know, there's zeros in that extension, and I can find a formula like the quadratic formula for the 5th order problem. But the thing is, people like Legendre, I think it was. No, not, I can't say words. Lagrange, right? Or if you're from Georgia, Lagrange. So Lagrange, you know, 1780, something like that time period in there, he tried very, very hard to come up with a 5th order and higher order analog for the quadratic formula. And he found like a systematic way of deriving quadratic and cubic and quartic formulas, some sort of really general idea about how to do it. And also focused on exploiting the things that I've talked about today, the symmetry between the roots, really looking at permutations between the roots, all right? And while Lagrange did not prove that it couldn't be done, people started to think, if Lagrange can't do it, and he spent decades on it, maybe it just can't be done. So in the early 19th century, about 1813, I think it was, Ruffini came up with a proof which people still debate whether or not is acceptable, that it couldn't be done. But then Abel, a little bit later, I think it's 1820, proved that there does not exist an analog of the quadratic formula for finding quintic roots. So he proved that it's not possible to find an analog for the quadratic. So like, that's a very kind of bizarre situation to be in, right? You have a proof that there exist roots, but you also have a proof that you can't write formulas for those roots down in terms of simple formulas like this. There's something different about those roots. And so then Galois came along about 1830 or so, and he extended the discussion further. He gave a further answer. He showed that by formalizing this observation that we made today about there being symmetries between the roots, you can define something for a given polynomial called the Galois group. And by studying the properties of that group, you can decide whether or not it's actually possible to find the roots in a radical extension in such a way that something analogous to the quadratic formula happens. And in a nutshell, what happens is if the Galois group is solvable, then something like the quadratic formula is possible for that one. But if the Galois group is not solvable, then no, it's not. You can't do it like we did it. It's not a Galois extension, as it's called. Ironically, one of the ways you can prove a Galois group is not solvable is by proving it's simple. Doesn't sound particularly simple what I'm describing, does it? But there you go. So that's where we're going this semester, is to try to understand that. So thanks for giving me an excuse to talk about something that high school people could understand today. Yeah. So let me get back on track now. You guys are supposed to know this, you know. This is like mad review right now. This right here. This is review. You're like, well, complex analysis is not a prerequisite. I know, but we do talk about nth roots of unity in 421. Am I right? Don't answer that.
No, it's true.
Okay. Proof by Morgan. I mean, wait a minute, no. Proof by Bethany. Let's see here. By the way, thank you for the free bowling. Yes. I did not anticipate Benjamin wanting to bowl, but
He was so good.
he won. Like I had the lowest score, and then I should have put. What I should have done is have bumpers. You know, if I had bumpers, it would have gone better. So the next section is on algebraic extensions. All right, that's what's up next. So some high points there. If we have K, which is over L, which is over F, right? So like, and suppose that this has degree P, and this has degree Q. In other words, suppose that the degree of K over L is equal to Q. Suppose that the degree of L over F is P, right? Then you put this together, the degree of K over F is what? Right, P times Q, because we have this calculation. And how did we prove that? Do you remember how we proved that last semester? Because this one I did last semester, because it's one of my favorites. It's pretty simple. So there's a basis, let's say basis equal to, let's say V1 dot VP here. And this would mean that there's a basis, let's say gamma, say F1 dot FQ up here. And if I recall correctly, you take something in K. So if we take, I don't know, I need some name, Pac-Man. If I take Pac-Man in K, that means that Pac-Man is equal to a sum of what? I equals, 1 to Q of C, I, Fi, right? Because remember the K is a degree Q extension over L, right? And then what we did was we said, oh, okay, well, we'll take that and we'll expand that. Where is this in? It's an element of, oh, excuse me. That's not what I want. That's not the point. What's the C? Where is C in? C is an L, right? And L is equal to the span over F of what? Beta. Which means we can expand Ci by a sum over j equals 1 to p of, let's say, b, I, j, and what do I put there? Oh, v, vj, fi. Of course, this is an element of the span over f of vj fi for 1 less than or equal to I less than or equal to u fill in the blank, 1 less than or equal to j less than or equal to u fill in the blank. Q at the top, P at the bottom. Yeah. And then we proved, okay, so that proves spanning. That proves that the, a basis for K over F is given to us by V, well, here, V1, F1, V1, F. How many Fs are there? Q. And then V2, F1, V2, FQ. And then finally, eventually, you get to VP, FQ, right? How many things are in this? Yeah, Q plus Q plus Q plus Q, P times, otherwise, PQ. And you can prove that that is linearly independent by appealing to the linear independence of both the gamma and the beta basis. And that proves this theorem, which is what? This theorem proves that a finite dimensional extension of a finite dimensional extension is finite dimensional extension. And what we learned in this section, the next section I'm going to put about algebraic extensions, is that there's a nice interplay between finite extensions and algebraic extensions. But we'll talk about that next time because I think I'm out of time. So thanks, guys. Of course, I never go more than a minute